Hello, friends. Today we are going to talk about how to do a two-sample t-test for the difference in means, which is section 11.2. So chapter 11 deals with hypothesis testing, otherwise known as test of significance, in regards to means. And remember, if it's in regards to means, we do t-tests. We use the t-distribution because, in general, we're not going to know what sigma is, and so we have to use s in its place. And so we have two estimates in each problem, and that being x bar and s, and that creates a t-distribution similar to a normal curve, as we've talked about several times now. But today what we're going to talk about is a two-sample situation. Whereas, in the last section we talked about we want to estimate a mu with an x bar, and so we'll use that x bar to establish or to find evidence for some sort of hypotheses in regards to mu. Someone says, well, I think the mean of, let's say, these test scores is 80, and the alternative is going to be, well, maybe not equal to a two-sided test, and we'll find an x bar. We take a sample of, let's say, 40 values, and we get a 75. Is that enough to reject the null? But what we're dealing with now in stats is a two-sample thing, because one of the things that's really interesting to us in stats is comparing two populations. And so we have this one population. Let's say it's the mean improvement of the people who took the drug. We have a new drug. We want to see if it works in lowering cholesterol. So mu sub 1. We are estimating that with an x bar sub 1. But we're also going to have a second population. Let's say this is the people that took the placebo. So all the people that take the placebo, and we're estimating that with an x bar sub 2. And we want to know if there's a difference between the two groups. Is there a difference between the mean improvement, those that took the drug, and those that took the placebo? Or in another setting, maybe these are the tomato plants that had the fertilizer and these had no fertilizer. Or this is the opinion of, let's say, the men in a city about some issue, and this is the opinion of the women in the city. We're very interested in stats. Is there a difference? And so our null hypothesis is going to be that there's no difference. So this is very similar to what we did in regards to proportions. So that is always going to be our null hypothesis in this section, is that the two population means are the same thing. And the alternative is what we suspect might be true or what we're testing for. And so if it says in the problem, we suspect, let's say, there's more improvement with those that took the drug, so we go greater than. Or we suspect that there's a higher test score in this school, so we would go less than. Like that. And so anyway, but it has to be stated in the problem. And so that's what we're doing. We want to see if there's evidence for a difference in two means. And so let's look at an example. We're going to look at three examples today. So a teacher wishes to see if there's a difference in the fifth grade students who learn math through a computer program and those that learn through the hard copy of a book. He takes a random sample of 40 fifth graders. We would certainly note that. That's important for a couple of reasons. In his district that go through the computer program. They show a mean improvement at 10.2 and a standard deviation of 4.6. And we know that mean is not a mu, that's an x bar, because it's a mean of the sample. The same thing. That is not a sigma, it's an s, because it's the standard deviation of that sample. He takes an SRS, that's also random, SRS of 50 fifth graders in his district and uses the hard copy of the book. They show a mean improvement at 9.6. That's another x bar. That is not a mu. Okay, and then with the standard deviation of 5.7, and that's the other S, the other standard deviation for the sample. It's not a sigma. All right, perform a test of significance to see if there's evidence for a difference in the mean improvement for the fifth graders who do the computer program and those that use the hard copy of the book. And so, all right, so here we go. So we're asked to perform a test, and so we'll follow our THAME acronym. So the first thing we have to do is state the type of inference, and this is sort of a long name, but it is what it is. It's a two-sample t-test for the difference in means, and that's kind of partially on your calculator, but it's what you have to do. And of course, if you write down the formula, you get credit for that, but it's probably easier just to write down the name. So you have to memorize that name. All right, so then we do our hypotheses, okay? And so here's our hypotheses. The null hypothesis is always that the two means are the same. The mean for the computer is the name for the mean for the book. And then the alternative, and of course define, you have to make sure and define what define your parameters. Mu sub C and mu sub B. Mu sub C is the mean improvement for the math scores for all the fifth graders in the district who went through the computer program. Mu sub B is for those that use the book. So it's the mean improvement. Nowhere up here does it say we suspect greater than or less than, or we think the computer would do better, or we think the book would do better. It doesn't say, so we go not equal to. Okay, so this is a two-sided test. The other way of writing this, by the way, you may recall from the section that we did with the two proportion z-test, is you could just say that their difference is 0. And a lot of times you'll see that in our book. So just subtracting mu sub b from both sides. And then the alternative would be that the alternative mu sub c minus mu sub b is not equal to 0. And if you're not good at writing mu's, then you can just write the word mu or write the word mean. So that's how you do your hypotheses. And this is just the same, very similar to what we've done in the past. We do our assumptions, otherwise known as our conditions, and that is our I sin. Okay, it's our I sin. Of course, randomness, it's still the same condition. It says they were randomly selected, so independent random conditions met. Whenever you have two sample things, you have to say independent random condition. So that's important. We've been doing that for a few chapters now. Our population sizes had at least 10 times our sample sizes for independence because we're not using sampling with replacement here. And so there must be at least 400 fifth graders, students who went through the computer program, and 500 using the books for our population sizes. There's two of them. Population sizes is greater than or equal to 10 times our sample sizes. That way our formula for our standard error will work. And then normality in this section, if both there's three possibilities, very similar to what we've done before. All right, if both sample sizes are greater than or equal to 30, you can just say, by the central limit theorem, normality is met. Or the second option would be, if you had small sample sizes, less than 30, if it's set up in the problem that it varies approximately normally, okay, both populations, then you would say normality is met. And the third one, and we'll look at that one in the next problem, is if a small sample size and it doesn't say it varies normally, you graph the sample data. And as long as you don't have outliers or strong skewness, then we'll say normality is reasonable. And all the problems we've had in the past few chapters in regards to each of these issues could be asked. It'll say, well, a question could be, what's the results of having sample sizes greater than 30? And you would say, oh, the sampling distribution of all possible differences will be approximately normal. Well, what's the product of the fact that our population sizes are at least 10 times our sample sizes? Oh, that assures independence and that we can use the formula for the standard error, just like we had in the past. So, all right. Now I'm going to show you the mechanics, which is a bit complicated, but yes, you can use your calculator to get your test statistic, your p-value, and your degrees of freedom. So let me show you. I'm going to, first of all, on your formulas, and you can use your calculator, but you do have to understand how to do this by hand, which I'm going to show you. So we have to find our test statistic. All right, so any test statistic on your formula sheet is statistic minus parameter over standard error of the statistic. Well, our statistic here, well, there's two of them, and we're going to subtract them. Okay, and our parameter is, in essence, just going to be 0. The standard error of the statistic, as you hopefully know, is on the next page, in the middle of the page, where it says standard error of the statistic, and there it is. It's sort of complicated, and it's a bit tedious, but it's not that bad. And so when we plug in those values, and so this is what our formula for our test statistic would be. You just subtract your two x bars, okay, which that's our x bar sub 1. That is our, that's 10.2, and that's our x bar sub 2. And then in the 4.6 and 5.7 are our standard deviations. And so you would get that value, and then you can use TCDF to get your p-value, and I demonstrated that in the last video that we have, and I won't do it right now. And then you can get this off of your calculator. But let me show you how to use your calculator, which is the main way you have to know how to do this. And so what we'll do, so the big calculator function in this section is this. We go stat, we go test, and this is a two-sample t-test. So there it is, option 4, two-sample t-test. And there's your name. That's most of it. So the name of this is a two-sample t-test, for the difference in means. So so we hit enter. Now this is stats. We weren't given data. We weren't given lists of numbers. So we're using stats. So we hit stats, and then we enter in our data here. And so our first mean, our first x bar is 10.2. So we go 10.2 like that. And then our first standard deviation is 4.6. So we go 4.6. And our first sample size is 40. Just like that. And then our second x bar, our second mean is 9.6 right there. 9.6. Our second standard deviation is 5.7, like that. And then our second sample size is 50, like that. And so our alternative, that's the alternative line, is not equal to. It's a two-sided test, as we say. Always say no to pooled when your calculator asks you for pooled. All right, and then we just go calculate, and there's our test statistic, a very small one, and there's our p-value, a very big one, and there's our degrees of freedom. Those are the three numbers you have to write, and that's all you have to do for your mechanics, is to write down those three numbers. Make sure to write down all three of them, including the degrees of freedom. And so that is what I have done here, in essence, is there's my test statistic, there's my p-value, and there's my degrees of freedom. So what the test statistic is basically saying is that these things are only about a half of a standard error from each other. It means they're not that far. And so this is saying that our 2x bars are relatively close to each other, so therefore it is plausible that the two population means are the same thing. It's not evidence for it, but it's plausible they're the same thing. So, and then this p-value, this conclusion here, is very similar to what we've had in the past. We've been doing it several chapters now. This p-value is greater than 0.05, a lot more. So I do not reject the null. There is not convincing evidence that mu sub c is not equal to mu sub b. Now, I ran out of space here, so I didn't say this in context. You've got to say it in context, and I'm sorry for that. I kind of don't like it that you have to define mu sub c and mu sub b twice, but anyway. So this is saying it is plausible that the mean score, the mean improvement for the computer kids is going to be this is going to be the same as the mean for the book kids. All right, and then here, and we've done this for a few chapters now. So create a 95% confidence interval for the difference in context 1. So that was in the last chapter we had. That was in chapter 10. So let's do that. Let's create a 95% confidence interval. So you remember we go stat and test and we go down to option 0, like that. And it actually already entered, and this was stats, and it already entered the stats for me. And so we're going 95% confidence, and we go like that, and boom, we have a 95% confidence interval for the difference. And so there it is. And so the connection between the interval and the p-value and the hypothesized value is this, is when the two-sample thing, the thing that is most interesting to us is 0 is in the interval, and so therefore it is a plausible value for the true difference. That would mean we're expecting a high p-value to tell us to not reject 0, which is in effect the null hypothesis value. So if 0 wasn't in the interval, that means it should be rejected at this level. And that would cause us to reject the null. So you need to get good at making that statement. So if you aren't good at it already. All right, let's look at our second example. That's how you do a two-sample t-test. But I want to look at a couple of other things that could potentially happen to you that are really similar sort of problems. And so you notice immediately in this case we're given the data. We're given lists of numbers. We aren't given the stats. And so that works out a little bit different with our calculator, but it's the same basic concept. We want to see if there's evidence for a difference in two population means. Okay, so it says a store manager wishes to see if customers who are warmly greeted when they walk in the store spend more money than those who are not greeted. She randomly selects 10 customers. Aha, we feel good about randomness, but 10 is not enough to guarantee normality by the central limit theorem. As they walk in, and has them warmly greeted. She then takes another random sample of 10 customers and makes sure that they are not greeted. She notes the amount of money that each of them spend shown below. Perform a hypothesis test to see if the people that are greeted spend more money on average than those who are not greeted. So here's the 10 people that walked in the store. That is how much money they spent of 10 people that were greeted when they walked in the store. That's how much they spent, and this is the people that were not greeted when they walked in the store. That's how much money they spent. And so, certainly these values are different, okay, if we were to average them. But that's not the real question. The real question is, are they statistically significantly different? So, so it asked us to perform a test, and this is a mean. Okay, so that means T, and we got two samples. So the name for this is the same as what it was on that last problem, is I'll do a two-sample t-test for the difference in means. So there you go. Memorize that name, please. Then, of course, the H of our THAME acronym is hypotheses. And so the null hypothesis is always going to be that your two means are the same. In this case, mu sub G is the mean money spent by all customers at the store that are greeted. And mu sub N is the mean money spent by all the customers at the store that are not greeted. Okay? So the null is always going to be those two mu's are equal. Okay? And the alternative is what we suspect might be true or what we're testing for. And up here, and you have to have a reason for it. So up here it says to test to see if they're greeted, spend more money than those that are not greeted. So that puts the greater than there. So this is a one-sided test. So there's your hypotheses. All right, so your conditions is the ISIN, a very similar sort of thing. Randomness, the same thing. It says they're randomly selected, thus independent random conditions met. There must be at least 100 customers that are greeted and 100 that are not greeted for our population sizes to be at least 10 times our sample sizes, and make sure our formula for standard error works. Now, in this case, our sample sizes are not bigger than 30. It doesn't say that things vary approximately normally, so we graph our sample data, which, by the way, you would graph your sample data anyway. But so we graph our sample data. I just plotted those points on a number line. You could have done a box and whisker plot or a histogram or a stem and leaf plot, but a dot plot works just fine. As long as you don't have outliers or strong skewness, we're going to say normality is reasonable. So the sample graph shows no outliers nor strong skewness, so normality is reasonable. That's the same thing we've had in the last chapter. This is identical, in fact, to what we had in the last chapter. So then in regards to our mechanics, so let me show you how to do that. So what you're going to do is you're going to get your test statistic p-value and degrees of freedom. I've given the data. I'm going to enter these in two lists, just like what we did in last chapter. Stat, edit, and in list 1 and 2, that's what I've done. So in list 1, I put those are the greeted amounts, and in list 2, I put the non-greeted amounts. All right, and then what you do, so to perform your test, you're going to go stat, you're going to go test, and you go down to a two-sample t-test, number 4. So this chapter is all about number 2 and number 4, by the way. So number 4, I hit enter. So I entered data this time. So list 1 and list 2, and then 1 and 1, that's good. The alternative in this case is greater than, so I go greater than. Always say no to pooled. And then we go calculate, and there is our test statistic, p-value, and degrees of freedom. And those are the 3 numbers. So there's your mechanics right there. So your mechanics are right there. Those 3 numbers, which you have to write all 3. Okay? So like that. And so then your ending, and it's the same p-value statement that we've been doing for a few chapters now. This p-value is greater than 0.05, so I do not reject the null. And I do not have convincing evidence that, and then you restate the alternative. Just restate, but you would state it in context. I kind of ran out of room here, and I'm sorry you have to do that, but please state it in context. But that's how you do the p-value statement, just like what we've done. All right, and so, all right, now, here's another auxiliary question that is a frequent auxiliary question. Probably the most popular auxiliary question, I think, would be to make the connection between the interval and the p-value and the hypothesized value, just like what we did in example 1. But it asked about type 1 or type 2 error. It says this: what type of error could we have committed in context 2, and what could be done to increase the power? Whenever you're asked about type 1 or type 2 error, this is what I encourage you to do. Of course, I said this in the last video. I immediately, so I won't get confused, I write down 1 is hot. I write down 1 is hot. Okay? Right like that. And so that reminds me that type 1 error, the null is true. You know, and it's an error, so I must have rejected it. I rejected the null. And so type 2 error is the vice versa of that. So type 2 error is when the null is false. Null is false. The null is false. And it's an error, so I must have failed to reject it. I failed to reject the null hypothesis. Okay? And so then power goes along with type 2. Power is a type 2 situation, but you do the right thing. Power is the null is false, and it is the probability that I reject it. So power is a conditional probability anyway. So what could we have done here? Now you notice here we did not reject the null. We did not reject the null. Well, and so it couldn't have been type 1 error. Type 1 error is when I falsely reject the null. But I didn't reject the null here. So I could have committed type 2 error. Could have committed type 2 error. And so that's what we will say here. Since we failed to reject the null, we are committing type 2 error if, in fact, the null is false. Okay, it would be type 2 error. And so one of two things is true. Either in fact the null really is true, all right, or we need more power. We need to increase our power to notice a true difference. And so how could we, whenever you get a high p-value frequently, they'll say, well, maybe we didn't have enough power. What can we do to increase our power? And there's two main things. You can increase your sample size, which here our sample sizes were only 10, so they were really small. Or you can increase alpha. You can increase your significance level from 0.05. And in fact, if you had increased alpha to 0.1 here to 10%, you would reject the null. Of course, the trade-off there is now you're going to have more type 1 error. So that's that. Now, another thing that I want to say to you is this, is being an important skill that we did, a couple of chapters ago that I want you to make sure that you understand. And that is being able to state type 1 and type 2 error, what they are in context. Like in this particular context, when it's talked about being greeted and being not greeted. So type 1 error is, once again, the null is true. In other words, there is no difference between how much money that the greeted people and the non-greeted people make. In other words, the greeting doesn't work, but I reject that and say that it does. So if you're asked in this situation, if you're asked to say, well, what is type 1 error in context? And so what you would say to yourself, well, you would just say, well, that means the null is true. In other words, when there is no difference between the greeted and not greeted customer spending, but I say the greeted spend more. In other words, I went with the alternative. And then what are the consequences of that? So the consequences of that, this means that I set up a system to greet customers, but it really doesn't work. So that is, stating or interpreting what type 1 error would be there. What would type 2 error be in context here? Well, type 2 error would be this. So type 2 error would be, say, when the greeted customers actually do spend more than the non-greeted. In other words, the alternative is actually true, but I say that they don't. In other words, I'm not rejecting the null for that. Okay? This means, and what are the consequences of that? This means I don't set up a system of greeting when I should have. Okay? So that's a popular question, stating type 1 and type 2 error in context. And then what is power in context here? Well, power in context means power is the probability that I'm going to reject a null hypothesis when it's false. And so power is the probability I will say that the greeting works given that it really does work. Okay? So that is type 1 and type 2 error in power. And those are very popular accessory problems that I wanted to remind you of. Okay, we've got one more example, and that one deals with the other thing that can happen. We had this happen last chapter, and so I wanted to remind you of this, and that is sort of a specialty sort of problem. And so let's look at this problem. You immediately, when you look at this problem, you notice, hey, we got a couple lists of numbers here. Okay, so this sort of smells like a two-sample t-test, and it's quantitative data, all right, and so anyway, it kind of smells like a two-sample t-test, but you always have to look, and is the data being paired? That is the big deal. So anyway, so it says a scientist wishes to see if a new mosquito repellent works better than an old repellent that is commonly used. He recruits 11 people for an experiment. It doesn't say how he got them, except that he recruited them. In other words, did he get them randomly? We don't know. All right. Each of the 11 people has the new repellent put on one hand and the old repellent put on the other hand. All right. For each person, it is randomly decided which hand gets which repellent. Okay. The subject then puts both hands into a box filled with mosquitoes for 5 minutes. I would not do this experiment, by the way, if I was asked to do it. But there's a reason why they didn't randomly select people, I think, because I'm not doing it. But anyway, the number of mosquito bites for each hand are listed below. Perform a test of significance to see if the new repellent works better than the old. What you have to read, so this is a person who, subject 1, he had the new repellent on one hand and the old repellent on the other hand, and he puts 2 hands into a box that has mosquitoes, and so the new repellent, only 12 mosquitoes bit it, and the old repellent, 28, and so forth for all the rest of these. Okay, you have to recognize this is paired data. This number goes with this number. You wouldn't be able to change the order of one of the lists. That would mess things up. And so whenever you have a paired situation and you're asked to perform a test, it is going to be a paired t-test that is in essence a one-sample test. Okay, so you're going to do a t-test with the differences. So whenever you have paired data, what we're going to do is this. We're going to subtract the two numbers. And you could subtract it either way, actually. You could say old minus new if you wanted. But I just subtracted that minus that, that minus that, that minus that, and got all of these differences. And now I do a one-sample t-test with the differences. It would not be correct to do a two-sample t-test here because we do not have independence. Whenever you have paired data, these are not independent random samples. Okay? Anyway, all right. So whenever, so we'll do. So the name of our test that we're going to do. This is a paired t-test for a true mean difference. That is the name of the paired t-test, and we're just going to do a t-test with the differences. All right. So our null hypothesis for the paired t-test is this: is that the mean of the differences is equal to 0. Okay. The null hypothesis is there's no change, no difference in the two. And if there's no difference in the two, in the long run, we're expecting the differences to be 0. Okay, that would mean that the new is not any better than the old if there was no difference. But if the new was better than the old, which is what we're testing for here, that means it would have less bytes. And so therefore, the new minus the old, we're expecting it to be negative. And I mean, just visually looking at it, all of them but one are negative. So it just, when you look at it, it looks like that the new one works better because all the differences are negative. But maybe we don't have enough power. Maybe we don't, in other words, maybe we need more to recruit more people to be involved in this. So your null hypothesis in a match paired t-test like this is that the mean of the differences is equal to 0. And then the alternative is what you suspect might be true. And if it didn't say something like better than or worse than or greater than or less than, you just put not equal to. And mu sub d is the true mean difference of the new minus the old repellent of the number of mosquito bites for people like these. And that's the other thing. We did not have random selection. So we can only generalize about people like these. We had random assignments on this thing. We have an experiment going on here. We did not have random selection. And so here's our assumptions, or otherwise known as our conditions. So it's, once again, I sin. But the first thing is this. Don't say they were randomly selected. They weren't. They were randomly assigned or randomly allocated, okay? It says the repellents were randomly assigned, where it said randomly decided. That's the same thing. So independent random condition is met for people like these. Whenever you have an experiment, whenever you don't have random selection, you have to say, for people like these or animals or things, whatever it is in the context, okay? All right, the second thing you notice, the population size being at least 10 times the sample size, we don't have to check that here because we don't have random selection. We are not sampling here from a larger population, okay? And so we don't have to check that, and we've done a few examples like that in the past. If you did check it, and if you did say, hey, there's got to be at least 110 people like this, then that's fine, but you don't have to do it, so I didn't write it out. The other thing is normality, all right? And so for the one sample deal, our sample size is going to be bigger than 30. It's not. It's only 11. Okay? Or it has to say that things vary approximately normally up here. It doesn't. All right? So therefore, you have to graph the differences. Graph the differences. All right? There are no outliers nor strong skewness in the data, so normality is reasonable. So that's what we're going to say, just like with the one sample t-test. All right? And so then what we would do is, all right, and here is, in essence, me showing the work. There's our formula, which is off of, in essence, your formula sheet, all right, to get that. But the way you're really going to do this is to use your calculator. And so what I did is I took these differences right here. I took these differences and I put them in a list, stat and edit, and I put them in list 4. I didn't want to mess up my other list. So there's all of the differences I put in list 4. And then going back to chapter 11, section 1, we're going to do a t-test with the differences, a one sample t-test. So I go stat, I go test, I go t-test, like that. And so I enter data in list 4, so I go with that, and then null hypothesis value is 0. All right, I put the data in list 4, frequency is 1, the alternative is less than, in this case. The alternative is less than. And so then I just go calculate, and there's your test statistic and p-value. So that is 3.655 times 10 to the negative fifth. Okay? So, and then that's a very small p-value. It's a very big t-score. So in essence, the difference between our sample mean and 0 is about 6.5 standard errors. So that is really very different. And so there you go. Make sure and write down. So you just have to write down these three numbers. You have to write down the degrees of freedom. You have to write down your test statistic, and you have to write down your p-value. Like that, which is that. So that's our p-value. And what this number means is 0.00004 zeros, all right, and 3.655, a very small p-value. Any reasonable value of alpha, you'd reject it. And so then we have our p-value statement, which is this right here, same as what it's been for a few chapters now. This p-value is below 0.05. So I reject the null, okay? There is convincing evidence that mu sub d is less than 0, and you have to say that in context. In other words, it appears, the answer in the question that's being asked, so to speak, it appears the new repellent works. I mean, not definitely, because it is possible, though very unlikely, that the difference is due to sampling variability. It appears the new repellent seems to work better than the old. So that's that. And really, the last thing I wanted to say to you is something that we've talked about before. All right, this here is what is known as drawing a conclusion from a p-value. That is different from interpreting a p-value. Interpreting a p-value is saying what it means in context. In other words, describing it as a probability. That's why we call it a p-value. And it is a conditional probability. A p-value is the probability of getting sample values this unusual given the null is true. Okay? So that is, in essence, your condition. And so interpreting the p-value in context here, and this happens in a problem in your assignment. And so the p-value is this: if there was no difference in the two repellents. In other words, if the null hypothesis is true, if we make that assumption and that there is no difference in the two repellents, all right, we would expect to get results this different about 0.003655%. In other words, that proportion, and I just moved it 2 decimal places to make a percent. So well less than 0.1% of the time. Okay, and so that is interpreting a p-value in context. Okay, that's it. Thanks for watching the video. I wish you all the best. I certainly encourage you to ask me any questions that you have in regards to this stuff. And I hope you have a great day.